All right, good afternoon, everybody. So this is a quick hitter video I've had in the works for a while here. And this won't take too long, hopefully, but I'm gonna show you how to measure your semi-angle of collection of your objective aperture, okay? Which is actually a very important parameter to know because it will help you select the right aperture for your specific intended TEM imaging application. So this becomes important, to make sure that you're getting optimal resolution. If you have a system without CS correction, usually you're looking for an aperture that has a very specific size so you can maximize your resolution. And so we're going to go over how to measure your semi-angle of collection of your objective apertures. So there's two approaches to do this, and they should give basically the same result. One of them basically requires that your camera length has been already calibrated, so your diffraction patterns are calibrated. The other one doesn't require that, but what it does require is that you have a sample with a known diffraction pattern with features with known D-spacing. You can do it with polycrystalline sample, but it works much better with a single crystal sample, okay? So we're going to go over both of these methods here, and I have a good sample for doing both of these because this is a silicon substrate, and this is E-beam platinum, and so we're going to see here how we can do this. Okay, so I already have the sample at eccentric height. I already have the zone axis roughly aligned. It's a 1, 1, 0 zone axis, the most studied zone axis ever. We can check the mono centering here. I just did this a couple minutes ago, so it should still be good to go. Oh, it's a little bit off. We'll go ahead and fix that. Okay, so I want to make sure that we are at eccentric height, so push eccentric focus and then focus with Z. Okay, so it looks like we're already pretty close there. Just want to be in the ballpark here. This doesn't have to be perfect for what we need to do here. Okay, that's good enough right there. Okay, and then we want, since we have a 3 condenser system, you want to spread your beam so you're in the you're solidly in the parallel regime. So something around 1.5, 2 microns should work fine for this. And then let's go into diffraction mode here. And we want to make sure that our direct spot is focused, so you can go to free control, go to the free control tab, activate MFY, find focus back focal plane, and make sure that your direct spot is focused. Okay, which we have it there, so we're good to go. Okay, and then I'm going to go back into image mode. And so let's talk about method 1 of doing this. So method 1 of doing this requires that your camera length has already been calibrated. You can do this at any camera length that you want. Usually like a longer one is going to be easier because your images of your aperture is going to be magnified more, but strictly speaking, you can do this at any camera length as long as it's calibrated. But you want to isolate the pattern from something that is weakly scattering, okay? It does have to be something. You can't do this just in vacuum. You can't do an image of your aperture just in vacuum because you won't be able to really see it. So you do need something. So this is E-beam platinum, and this will work perfectly for this, okay? So I'm going to isolate this with a selected area aperture. And so we'll go to, let's use the 40 here. Okay, and then I'm going to move the sample so only the PT is inside of the aperture. And then we'll switch to diffraction mode. Let me switch to turn off high resolution. And then I'll go ahead and center my direct spot. Center my pattern. Okay, and now I'm going to insert the objective aperture that I want to measure. Okay, so let's put in the 50 here. We'll put in a larger one to make this easier. And now let me switch to HDR mode, and let me switch to, okay, you can kind of see this. So now I'm going to, you can see we're not quite centered, but I'm going to deliberately translate this so the direct beam is not included, okay, because it's going to make it easier to see my aperture edge here. So let me switch to natural. Perfect. Okay, so that's much easier to see. Okay, all right. But of course, this requires a calibrated camera link, so we actually have to image this with the SATA camera. Okay, so I'm going to go to acquisition mode. I'm going to drop my exposure time down to the minimum for my camera, which in this case is 25 milliseconds. Then we'll start the view. Okay, we'll take the screen out of the way, and there we go. So my max counts is very low, so I can increase this. Okay, so let me check this. I've got this set for 2 seconds, 1 frame. That should be fine. I can clearly see the edge. The other thing, of course, too, is when you're seeing the edge of the aperture, you want to make sure that it's sharp and in focus. So if necessary, you can use your diffraction stigmator to focus the aperture edge, and then focus with your focus knob when you're in diffraction mode. This looks fine right now, so I'm not going to adjust it. But if it looked blurry, those are the two things you would want to check: your diffraction focus, and then your diffraction stigmators, and then your diffraction focus. But that looks fine. All right, so I'm going to go ahead and do an acquire, and then we will move over to processing mode. Put the screen back in, blank the beam. Okay, so now we can see very clearly the aperture edge, and again, this has been calibrated, so this scale bar is now meaningful, okay? So if I draw an annotation here, and we want to use a circle, hold down Shift, and that will constrain your annotation to be a circle. I'm going to change the color of this. I don't like this green color. Will it let me change it? Yes, it will. I'm going to change it to, yes, I like that cyan color. But anyways, whoops, hold down Shift, and then you want to adjust this until it fits your objective aperture. You can fudge with your gamma here to make it more obvious. You can digitally zoom in, right? So you want to adjust this so the fit is good. You can probably scale this down just a smidge more. Okay, that looks good right there. All right, so now go over to your object properties. And what's my radius? My radius is 6.652 reciprocal nanometers. Now, of course, there's some leeway here with how you measure this. I could probably cut this down, again, just a little bit more. Yeah, we'll call it there. Okay, so we'll call it 6.16 reciprocal nanometers. That's the radius. So if I wanted to get this answer in terms of an angle, I have to multiply this by the wavelength in nanometers. So, whoops, we're going to use that later, but for now we'll just pull up the calculator. So we have 6.616 times 0.00251, which is the wavelength at 200 kilovolts in nanometers. And what it's saying is my semi-angle of collection is 0.166 radians, or 16.6 millirad. Okay? So that's the size of the semi-angle of collection for my 50 micron objective aperture. So now once you have this size calculated for one aperture, you can in principle just extract or extrapolate to all the other apertures based on a ratio of the sizes. So in other words, if I want to know what the semi-angle of collection is for the 40, I just have to multiply this number by the quotient of 40 and 50. Okay. Same thing if I want to know the semi-angle of collection for the 60, I have to multiply it by the quotient of 60 and 50 in that case. In practice, it's a little bit more accurate to actually put those apertures in and measure them because there's some variation in the size of this, and they're often not perfectly the exact diameter shown here, but they are very close because I have actually measured these experimentally. Okay? All right. So that is method one, with your camera length being calibrated. So now, what are we going to do if our camera length is not calibrated? And so in that case, we need to rely on having a sample with a known diffraction pattern. Okay, so I'm going to go ahead and unblank my beam. I'm going to take my objective out. Let me switch back to grayscale for the moment, and we'll go back to image mode. And now I'm going to move into the silicon substrate, and I'm going to isolate. I could go a little farther down here, but I'm actually just going to change my SA aperture to be the next size down. Okay, and we're isolating just the silicon, and now we can go back into diffraction mode. And now there's really no, again, we're assuming, right? We're assuming that we're not calibrated on the SATA camera. So there's no point in putting this on the SATA camera. We can just do this on the FluCam. Okay? So we'll switch this to HDR, and I'm going to switch this also to temperature. And let's put the same aperture back in because we should get the same answer for each one of these methods of doing the measurement. So let me go ahead and adjust this and move it over here. So yes, hopefully you can very clearly see the aperture there. This is much easier in temperature range than in grayscale because, as I've said many times before, your eyes are sensitive to millions of colors, but we're only sensitive to about 25 to 30 shades of gray. Okay, so what do we do now? Let me switch to high resolution mode, and let me turn off the screen markings. So now, what we have to do here is we have to know the D spacing corresponding to one of these spots. Okay, so this is the most studied zone axis ever, 110 for silicon. So I know that these four closest spots, these are all 111 spots. Okay, these right here are kinematically forbidden 200, and these out here are 220. These right here are, I believe, what would those be? These would be 113 spots here, okay? So in principle, it's actually, if you can measure a larger distance in the pattern, that should give you a more accurate answer here, okay? So basically, if we're going to use these, now actually what we could do, this isn't quite centered, so let's use these 113 spots here instead, because this is a little bit off here, but we can clearly see the distance here, okay? So what we're going to do then is, first of all, we need to calculate the D spacing, okay? So the lattice constant of silicon is 0.54 nanometers, okay? So then D113 equals 0.54 divided by square root of 3 squared, plus 1 squared plus 1 squared equals, let's break out the calculator here. All right, so we've got 0.543 divided by, where are you, square root? Where is it? There isn't a square root here? Oh, it is. Okay, there we go. Oops. All right, we'll have to do this a little more. Let me clear this here. All right, so we'll do 11 square root. Okay, so that's 3.132. We'll divide by 0.543 and then take the reciprocal of that. So yes, so we get 0.164 nanometers. Let me expand this a little bit more. Okay, so what that means then is if we take the reciprocal of that, we're going to get this distance in reciprocal length units. Okay? So what we can do then is we can measure this distance here. And now, depending on the FluCam, I believe it's going to use millirad for this. But again, this isn't calibrated, so I'm just going to have to position this. That looks good. So it's saying we have 28.1 millirad. So the distance in the pattern, so we'll call this R113, is equal to 28.1 divided by 2, because we took twice the distance. And that's going to be 14.05. And I'll put millirad in quotations because that's just the indicated units. Okay, so then we'll call G113, right, because that's the reciprocal of the D spacing. That is equal to the reciprocal of 0.164. So we have 1 divided by 0.164 equals 6.0. We'll round it to 6.10 reciprocal nanometers. Okay. All right. So now we need to also measure the radius of the aperture. So we'll call this radius aperture again in the millirad units. So let's use the ellipse annotation here, just like we did when we were working with the FluCam, because this is going to be a little bit more accurate than actually measuring just with the line. So let's see here. This is in dual. Let me put the beam stop in here. Let's see if we switch to manual, if I can increase this at all. It's already there. I can integrate. No, I can't integrate more frames. Let's see, if we switch to natural, yeah, I guess it looks better in just HDR mode here. Okay, well, it really didn't help a whole lot. So, all right, so we can just eyeball this here again. That's what we're gonna have to do. All right, that looks pretty good though. You can see the aperture is maybe a little bit displaced from center, which is again not a big problem. I mean, the size is irrespective of where it's placed, but it's telling us that the diameter is 30.7. Okay, so there our aperture is 30.7 divided by 2, and that's going to give us 15.35, again, millirad in quotation marks. Okay, so now if I want to figure out the reciprocal or the radius of the aperture in reciprocal length units, I simply have to multiply G113 by R aperture divided by R113, okay? So if I do G aperture, that's equal to 15.35 divided by 14.05 times 6.16 equals, so I don't know why I deleted that because I was still going to need it, 6.1 times 15.35, whoops, divided by 14.05. Okay, and it's giving us 6.66 reciprocal nanometers. And now again, if we want to convert that to a semi-angle of collection, so we'll call that beta aperture, that's equal to 6.66 times 0.00251, which is the wavelength in nanometers. Okay, and we can see that we get basically the same answer that we got using the initial method where we measured the radius, or the radius of the aperture on the SATA camera. And you can see the discrepancy is only 1/10 of a millirad, okay? And so if we were to measure that in terms of a relative error, 16.6, so that's basically a 1% difference with this measurement method compared to the previous measurement method. So both methods give us the exact same answer, okay? So that's a crash course in how to measure the semi-angle of collection of your objective apertures. And again, this is useful for figuring out which aperture you're trying to use if you're trying to maximize, say, your point spread or your point-to-point resolution. If you have a system without CS correction, depending on what your aberration coefficients are, that's probably the most relevant application. So that concludes the video. I hope you found it useful, and I'll see you again soon.